6. A tank has the shape of an inverted circular cone with a height of 10 meters and a base radius 4 meters. So let's first of all draw the tank. So the tank is right here. It's got an inverted cone, which means that the base is going up and the point is going down. The base radius is 4 meters. And the height of the cone is 10 meters. That is made of some sort of material that's going to be there forever. So that's not going to change. That's the tank. It always is the tank, and that's how big it is. And let's just make it a little different color here. Let's go with a red tank. Does that make sense? You see a bunch of red water tanks out there, right? It's filled with water to a height of 8 meters. So the current state of the tank is we got water right here, and it's 8 meters high. I don't want to write the 8 in, though, because we're going to be draining the tank. So the height of the water is going to change. And what I want to imagine here is if we were to draw an XY axis where the water is going to be emptying out. Let's see. That way. That looks good. So I want the water to empty out of the top of the tank. So the water is going to be going this way, going up to get out. And I called it an XY axis. Let's just consider like we have just like a coordinate axis there. All right, I need to pick a variable to represent this, how far the water is away from the emptying spot. Okay, so it's being emptied right here at 0. Let's just, for the sake of having a variable, call it x. Let's say x is how far the water is away from 0. All right? So once we establish the distance between the spout where the water is going out to the top of the water is our variable, then this water height itself is going to be something based on that. So we know from here to here is 10, right? Mm-hmm. And this is x, so what's left over will be 10 minus x. And if we consider that, if I take this piece 10 minus x, add this piece x, I'm going to get 10, right? So that's kind of, you can see that right there. You always want the distance from the spout to the water top to be x, and from the water top to the bottom of the tank to be whatever the height is from here to here minus x. Okay. Sometimes the spout's right there, sometimes it's up above. Maybe it's 3 or 4 feet above. If it was 3 feet above, then x would still be here. Now this would be 13 minus x. All right, so depending on how far that spout is, the water has to travel up. It's going against gravity, so it's creating more work the higher it has to be. Okay, so the top, where the spout is 0. From the spout to the top of the water is x. And the top of the water to the bottom is how far it is, this minus x. Make sense?
Mm-hmm.
Okay. Now, what we're going to do here, and this is the part that I find to be a little bit challenging, is we're going to construct a cross-section of this thing, and we're going to find the work it takes to do that. And then we're going to integrate that work in order to find the answer. All right? And it bothers some people here about doing this, but let me just show you what's going on. And I've got a lot of stuff going on in there, so that's part of the process of why this problem is a little difficult, because it gets a little bit hard to see things. All right. So I just, for the sake of being able to see, but I just want to draw it one more time. All right. And I'm just going to put the top of the water there. I'm not going to fill in the water. All right. Imagine that there's some disk of water in this cone. So if I were to slice this cone somewhere, it's going to make a circle, right? Right. Imagine that circle of water, and it's going to have negligible height, but we're going to give it a little bit of height. There we go. If I were to slice out a little cross section of this like that, that makes a circular disc, right? It's not a cone because this is negligible. So it basically just, it would be just like a washer or maybe a coin. Imagine a coin. It's circular, it has a little bit of width to it, right? So we're slicing a dime or a quarter or a nickel out of this thing, right? The radius is right here of that. And the height of this disk I'm going to call delta x. Now looking at some specifics in this problem, I know from here to here, from where the water is to the bottom of the tank is being denoted by 10 minus x from the picture up here. So that length is 10 minus x. So looking at this triangle here, we have a radius of the disk. We have a height of 10 minus x here. And we have that there. And then looking at the entire thing, we have a radius of 4, we have a height of 10, and we have a hypotenuse here, right? We have those overlapping triangles. The importance here is not, you see, I'm worried about this disk. I'm not worried about the whole cone of water. I'm worried about the disk. But I really need that radius to be in terms of x. So what I'm looking at here is similar triangles. 4, 10, 10 minus x, and r are going to be proportional to each other. I know that if I do 4 over 10 from the bigger triangle, that's going to match up to 4 goes with radius and 10 goes with height. 10 minus x. If I cross multiply that, or before I even cross multiply, notice 4 tenths reduces to 2/5. Reducing is helpful. Okay. If I cross multiply, I get 2 times 10 minus x equals 5r. Divide both sides by 5, and I get that. Recommendation, leave 10 minus x in parentheses. Makes the problem easier. Okay. Every time you do these problems, you're going to usually get something along those lines. There's going to be some number minus x in there. Just leave it all by itself in there each time. Makes it easier. Is everybody comfortable with what I've done so far? So now if we're looking at the circular cross-section, we try and find the volume of this circular cross-section. Volume of a cylinder, which is what that is, circle, circle, height, right? Just a circular cylinder, is the area of the base times the height. The height of the cylinder is delta x, and the radius is this. We do pi times that squared times the height. The volume of my cylinder ends up being this. Pi times r squared times height. Looks like that. So, that's job one. Create a cross-section and figure out what the volume is of that cross-section in terms of whatever variable you want to use to represent the water moving. So I like to use x. I find x to be a nice little variable to use, so I usually use x. But I want everything in terms of x for my volume of this cross-section. Height's going to be delta x every time. You're more worried about the geometric shape here. This is a circle. I gave you a homework problem with a rectangle. I think I gave you 3 with a rectangle, 1 with a circle. So for a rectangle, you need length and width both in terms of x. Height's going to be delta x. For a circle, you need radius in terms of x. Height's going to be delta x. Renee?
How do you know, like, when you're doing your, like, your fractions and you have to cross multiply, how do you know which numbers to put where?
Okay, well, I just know that if I'm cross multiplying, I'm going to do that product equals that product, right? So 5 got multiplied by r, and 2 got multiplied by 10 minus x. My job is to figure out what r equals in terms of x. So I want r equals something else. So I want to solve for r, so I divide by 5 to make that happen. If I want to know what x equaled, I'd have to multiply that out, then figure out what x equals. But I'm going to be using delta x here, so I want to make sure I got r in terms of x there. That's how you establish that. So each time you do it, again, I just use x every time so I don't get confused, personally. I just, if I'm always using x, I know I always want everything in terms of x. I always get the other letter equals something about x each time. That's what I do to avoid confusion for myself when I'm doing these. All right? So my volume's right here. Now, my goal again is I'm going to try to integrate a work expression. Volume is not work. Volume is just how much volume is in the water of this little disc here, right? So, next thing I need to do is I need to find this is cubic meters, right? I need to find the mass of the water. And you can see here the density of the water is 1,000 kilograms per cubic meter. So we have cubic meters of volume, right? If I multiply cubic meters times kilograms over cubic meters, that gets me kilograms. That'll be the mass of this disk of water. Okay? So what I need to do is, again, this is meters cubed. So I'm going to take this whole thing times 1,000 kilograms per meter cubed. Meters cubed cancels meters cubed. The unit left is kilograms. That'll be the mass. So now the mass of the water is equal to. Now, it gets a little messy in here. You can see that we got lots of stuff going on. 10 minus x in parentheses squared is a binomial squared structure. Everything else is just a bunch of single objects. One thing times a fraction, one thing, delta x, one thing, 1,000, one thing. All those single objects multiply together. So 2/5 times 1,000, if I were just to do that right there, and multiply it all out, I'm going to get, oh, why did I have 2/5? It should be, no, that's right, never mind. Oh, wait, I know what's wrong. Sorry. I knew something went wrong. Hold on, sorry. This should be 4/25. Let me show why. This is the radius, right? We're supposed to square the radius.
Oh, okay.
2 squared, 5 squared, 10 minus x squared. I didn't square the whole radius, I just squared that part. So square every piece of this little thing here when you do pi r squared. So 2 squared, 4, 5 squared, 25. I knew it was supposed to be 400, so I knew something was going wrong there. So let me fix that. Challenging as promised, right? All right, so single object, binomial squared, leave it by itself, delta x single object, 1,000 single object. So this 25 goes into this 1,000 40 times. Pi times 4 times 40 makes 160 pi times 10 minus x, the quantity squared, delta x, kilograms. It may be helpful to you as you go through this to really identify things as what they are. This right here is the volume. The volume is in cubic meters. Multiply volume times density, cubic meters cancel, so we have mass now, which equals kilograms. So you always go volume first, use the density to find mass. Then mass times acceleration, and we're dealing with Earth here, right? We're assuming the tank's on Earth, we're not on the moon or Jupiter or something weird like that. So we're on Earth emptying this tank. So the gravitational force of Earth is 9.8 meters per second squared. So if I take mass times acceleration of Earth, which is times 9.8 meters per second squared, that gets me a force. 160 times 9.8 is 1,568. So again, single object, single object, single object, all that. This binomial is going to be left alone. So 1,568 pi times 10 minus x squared delta x. Kilograms meters per second squared, also known as newtons. So now we have the force in newtons. And finally, I want to find work. All right? I want to integrate work. Now, yesterday we did these work problems. We were integrating force to find the work. On these problems specifically, when you do this little cross-sectional thing here, you're going to be integrating the work to find work. I wish I knew why. I just know you're supposed to do it. So this is one of those Nike rules here. Just do it. You're supposed to multiply times height on this one. All right, so the water is going a distance of x units wherever it's at, right? So if I'm here, it's going x, x is 2. If I'm here, it's going x, x is 5. If I'm here, x is, how much is going? X is 8. So as the water moves, x is getting bigger, right? But it's moving x units. So the work in this case is simply going to be all this stuff times x meters. Newton meters is joules, right? So we're going to get 1,568 pi x times 10 minus x squared delta x joules. The hardest part about that is I don't know why we're supposed to do it. But if just have faith you're supposed to do it, the right answer is going to be coming out on your paper. All right? So whatever you get for force, just stick an X in there. Now you got work. All right? Because again, each time you're doing it, we're going to construct it every time that X is always the distance from the spout to the top of the water, so the water is always going to be moving X units. You always stick an X there. All right. I'm going to move to a new page now. All right. So what I want to integrate then is my work function. So I'm going to integrate 1568 pi x times 10 minus x, the quantity squared, delta x. So delta x becomes dx. All right? So the delta x has been coming along for the ride all this time is dx. All right? And if we take a look at our picture, this is where x starts, x equals 2, and this is where x ends, x equals 10. Again, the distance from 0 to the top of the water, 2 spaces, from 0 to the bottom of the water, 10 spaces. So wherever the spout is, and again, the spout's above the tank somewhere, so you have to go up even extra, 0 to the top of the water, 0 to the bottom of the water. How far is it? That's what x represents. So my interval goes from 2 to 10. That interval right there is going to give me the answer to the problem. The challenge of the problem is creating that integral. Once you've created the integral, evaluating the integrals is what it has been. You anti-differentiate, you stick your numbers in, you work it out, you get your answer. So I'm going to go over to that page only. That's huge. All right. So my x objects are right here. That's what I'm really integrating. The 1568 pi is just a number, right? So I'm going to pull that number out of the integral just to make it look a little easier to deal with. So work is going to equal 1,568 pi, integral from 2 to 10. Okay, now I want to multiply this out now. So x parentheses 100 minus 20x plus x squared dx. If I distribute the x through, I'm going to get 100x minus 20x squared plus x cubed dx. And finally, now it's a polynomial structure. I simply anti-differentiate. I'm going to get 50x squared increased by 2 divided by 2, or sorry, increased by 1 divided by 2. So 100 divided by 2 is 50. Increase this by 1 becomes 3, so I'm going to get 20x cubed over 3. That doesn't divide evenly, so I'm going to leave as a fraction. That's going to be x to the 4th over 4. That whole thing is being multiplied by 1568 pi. So I'll put 10 in, put 2 in, subtract the 2 results, get your answer. So I'm going to type in 50 times 100 minus 20 times 1,000 divided by 3 plus 10,000 divided by 4. I'm going to hit math frac, enter. Oh good, comes out. If it comes out to a nice pretty fraction, fine. If it gets to be like, I think if it's 5 digits on top or bottom, it doesn't create a fraction for you, but as long as it's 4 digits, it allows. So 2,500 thirds. If at some point we start getting decimals, that's fine, but I'm going to try and avoid it as much as possible. If I put 2 in, I'm going to get 50 times 2 squared, which is 4, minus 20 times 2 cubed, which is 8 divided by 3, plus 2 to the 4th, 16 divided by 4, comes out to 16 divided by 4. Math, frac, enter, 452 thirds. Alright, so if I subtract those, I'm going to get 2,048 thirds. So then it's just a matter of multiplying it out. Obviously pi is going to give me a decimal number, right? I want to leave pi in the answer, I could, but I just go ahead and get a decimal answer on these is fine. So if I type in 1568 pi times 2048 thirds, thirds comes out to 3,362,827.797. So I'm gonna go 3,362,827.797.